Why anyone who goes to Neptune will never come back. Tonight, we're going to talk about a planet that is hotter on the inside than it has any right to be. And this single fact is what kills anyone who tries to leave. The cloud tops of Neptune are minus 221 degrees Celsius. The core is over 5,000 Kelvin, nearly as hot as the surface of the sun. Between those two layers is everything that makes Neptune impossible to escape. We're not going to talk about ice. We're going to talk about the wall. I want to be careful here, because the standard documentary version of Neptune is wrong in a specific way. It tells you Neptune is cold, distant, and quiet. The truth is that Neptune is the most violent planet in the solar system. The fastest winds, the strangest internal heat, the layer where it rains real diamond, the mantle of water that conducts electricity at 5,000 degrees. And under all of that, a core that does not care what you brought with you. In this video, we are going to walk through 14 specific reasons Neptune may be the cleanest one-way door in the outer solar system. We will look at the energy budget. We will look at the supersonic atmosphere. We will look at the diamond layer, confirmed by laser experiments in 2017. We will look at the superionic ice, confirmed by Lawrence Livermore in 2018. And we will look at the escape velocity that no rocket we have ever built could meet from inside the planet's clouds. By the end of tonight, you will understand why Neptune does not let people leave. If you enjoy what we do here, hit like and subscribe. Tell me in the comments where you are tuning in from tonight. It makes a real difference. Now, we start. The planet at the end of the map, most people, if you ask them about Neptune, will tell you something close to the same answer. It is the 8th planet. It is far away. It is blue. It is cold. The textbooks gave us this picture in elementary school, and most of us never updated it. Neptune sits at the edge of every diagram of the solar system, drawn in a faded shade of cyan, often smaller than it should be, and the line of explanation usually ends there. This is the version of Neptune that almost everybody carries in their head. A distant blue ball, a name on a list, a planet that exists, technically, but does not really do anything. I want you to forget that picture. I want you to forget it carefully and completely, because the version of Neptune we're going to look at tonight is not the version on the diagram. The version on the diagram is a polite lie of perspective, drawn for 9-year-olds, designed to fit inside a poster. The actual planet, the one out there in the dark right now, is one of the most extreme objects in our solar system. It is one of the most extreme objects we have ever measured anywhere. Let me give you the basic numbers, and then we will start undoing what they actually mean. Neptune is roughly 30 times farther from the Sun than the Earth is. It sits at about 30 astronomical units of distance, which works out to around 4.5 billion kilometers. That number is so large it stops meaning anything when you say it out loud. So let me give you a more useful version. Light, the fastest thing in the universe, takes more than 4 hours to travel from the Sun to Neptune. The same light that warms your face on a summer afternoon, by the time it reaches Neptune, has been traveling for over 4 hours and has spread out across so much empty space that it is almost gone. The amount of sunlight that reaches Neptune is roughly 1/900th of what reaches Earth. 1/900th. The Sun from Neptune is not a fireball. It is a bright pinpoint, only about as wide in the sky as a grain of rice held at arm's length. There's a phrase NASA uses for this. They say that high noon on Neptune would look to us like dim twilight. The brightest moment of the brightest day of the brightest year on Neptune is darker than the moment just after sunset on Earth. This is where most people stop. Cold, dark, far. Got it. But this is exactly where the planet starts becoming impossible. Because here is the part that almost nobody mentions. Despite receiving 1/900th of Earth's sunlight, despite sitting in functional twilight for the entire 14-hour day, Neptune has the fastest winds in the solar system. Faster than Jupiter's. Faster than Saturn's. Faster than anything ever recorded on Earth. Wind speeds on Neptune have been clocked at over 2,000 kilometers per hour. 2,100 kilometers per hour, supersonic flow. Faster than the speed of sound through Neptune's atmosphere by a factor of 1.5. Stop and feel that for a moment. The planet that gets almost no energy from the Sun has the most violent weather in the solar system. That is the first crack in the picture you arrived with. The cold blue ball at the edge of the diagram is not quiet. It is not still. It is moving faster than any aircraft humanity has ever flown atmospherically, and it is doing it in temperatures that should not allow for that kind of energy at all. And the wind is just a surface layer. Beneath the cloud tops, the planet does things to matter that we did not even know were possible until labs on Earth recreated the conditions in 2017 and 2018. Carbon turns into diamond inside Neptune. Water turns into a phase of matter scientists predicted decades ago, but only recently confirmed in the laboratory, a phase that conducts electricity, that flows like the mantle of the Earth, that does not behave like ice or liquid or gas. The core is nearly as hot as the surface of the sun. The pressure is greater than at the center of our own planet, and there is no surface to land on, anywhere, at all. I want to be careful with how I phrase the next sentence, because it sounds like a metaphor, and it is not. It is a description. Neptune may be the cleanest one-way door in the outer solar system. The geometry of the gravity, the chemistry of the atmosphere, the physics of the heat, all of it conspires the same way. Anything that arrives for good. Anything that survives the descent never comes back the way it came. There's a reason Neptune has only ever been visited once. There's a reason no probe has been there in 36 years. There's a reason no probe is currently on its way. And there's a reason the few mission proposals that have been submitted to NASA in the last decade have all stalled in committee. The reason is not one thing. It is distance, cost, launch windows, power, risk, and the planet itself. Over the next 14 sections, we are going to walk through the specific physics, layer by layer, that make Neptune the only one-way door in the solar system. We will start with the energy budget that does not add up. We will move to the supersonic atmosphere. We will descend through the crust layer, through the diamond rain, through the superionic mantle, all the way to the core. And then we will come back out. Look at Voyager 2. Look at Triton. Look at the communication delay, and finally look at the gap of silence, where we have not gone back, and the reason that gap exists. By the end, you will understand why this planet, the one almost nobody thinks about, is the place we will probably never reach again. But first, we have to talk about the energy, because the energy is where the lie starts. The energy that should not be there if you sat down with a sheet of paper and tried to predict, from first principles, what Neptune should look like. You would get most of it wrong. And the part you would get most wrong is the weather. Here is the basic logic. Sunlight at Neptune is 1/900th of what we get on Earth. That number is not a guess. It is geometry. Light spreads out as it travels. The intensity drops with the square of distance, and Neptune sits at 30 astronomical units. Run the math. Whatever sunlight reaches Earth, divide it by 900. That is what Neptune has to work with. On Earth, the sun is what drives all of our weather. The temperature gradients between the equator and the poles, the rising warm air, the falling cold air, the jet stream, the hurricanes, all of it is solar energy being moved around by the atmosphere. If you took the sun away tomorrow, the weather would stop within days. So a planet with 1/900th the energy budget should have, all else being equal, almost no weather at all. The atmosphere should be still. The clouds should not move much. The temperature differences across the planet should be small, because there's not enough energy to drive large differences. That is the prediction, and it is wrong. Neptune has the fastest sustained winds of any planet in the solar system. The cloud tracks measured by Voyager 2 in 1989, and confirmed by ground-based observations and Hubble in the decades since, show wind speeds reaching roughly 2,100 kilometers per hour at the equator. That is 600 meters per second. That is faster than the speed of sound through Neptune's atmosphere. It is faster than any military aircraft on Earth has ever flown sustained at sea level. It is, in raw atmospheric energy terms, a planet with a hurricane that never ends and never weakens. And it does not have the energy to do this. Not from the sun. I want to be careful here, because this is one of those facts where the explanation is genuinely contested. Multiple research teams have proposed different mechanisms. None of them is fully accepted. The current best guess, supported by published work in 1991 and refined through follow-up studies, is that the winds are driven by deep convection, by heat rising from the inside of the planet rather than coming down from the sun. The atmosphere is being stirred from below, which is interesting because it means the energy is not coming from where we expect. Neptune radiates 2.5 times as much heat as it receives from the Sun, 2.61 times, to be precise, based on the most recent measurements. For comparison, Uranus, the planet right next to Neptune in size and composition, only radiates 1.1 times what it receives. Same kind of planet, same kind of distance, same kind of formation history, and yet Neptune is throwing off more than twice the energy of its near twin. Where is that extra energy coming from? Nobody knows. Not really. There are theories. One theory says that Neptune is still cooling from its formation, that the heat trapped during its accretion 4.5 billion years ago has not had time to escape yet. Another theory says that the planet is undergoing slow gravitational compression, that material is still settling toward the core and releasing heat as it falls. A third theory points to chemical processes in the deep interior, possibly the precipitation of helium or some other element, releasing latent heat as it separates out. All three may be partially correct. None of them is settled. What is settled is the measurement. Neptune is hot inside, hotter than it should be, hotter than its sister planet Uranus, which by every other measure should be the warmer of the two. Uranus is closer to the Sun. Uranus has the same mass. Uranus has the same age, and yet Uranus is colder. Neptune is the anomaly. This matters because it tells you something important about what kind of object you are actually looking at when you look at Neptune. You are not looking at a quiet, cold, distant planet running on a thin sip of sunlight. You are looking at an internally powered engine, a self-heating world, a planet that runs on its own internal energy, separately from the Sun, and that internal energy is enough to drive the most extreme weather we have ever measured anywhere. Now think about what that means for anything trying to descend through it. If the Sun goes out tomorrow, Neptune barely notices. The clouds keep moving. The winds keep blowing. The internal furnace keeps burning because it was barely using the Sun in the first place. Whatever drives Neptune's atmosphere is locked inside the planet itself, and it has been running for at least 4 billion years, and it shows no signs of running out. The deeper you descend into a planet like that, the more you are descending into the engine itself, not into a calm interior, not into a still core. You are descending into the source. Most planets get colder and quieter as you go down. Neptune gets hotter and more violent, and that is the second crack in the picture. The cold blue ball is not running on starlight. It is running on something it carries inside. We still do not know what that something is, and we are about to descend into it, faster than sound. In the dark, let me give you a physical picture of what 2,100 kilometers per hour actually means, because the number is so big it stops feeling real. On Earth, the fastest wind ever recorded at the surface was during a tropical cyclone called Olivia in 1996, off the coast of Australia. The instrument logged a gust of 408 kilometers per hour. That single gust, lasting seconds, is the fastest wind humans have ever measured at the surface of our planet. It tore the anemometer apart shortly after recording it. Neptune's wind is over 5 times faster than that, and it is not a gust. It is sustained. It blows around the planet, day after day, century after century, for as long as we have been able to measure it. If you stood at the equator of Neptune, on a platform somehow capable of surviving the temperature and pressure, the air would be moving past you at 600 meters per second. That is 1.5 times faster than the speed of sound through that atmosphere. You would not hear the wind. The wind would arrive before any sound it could make. The first thing your ears would register would be the impact, not the noise. If you try to imagine an Earth equivalent, you could not. There is no Earth equivalent. The closest analogy is the air that rushes past a fighter jet flying low. But the fighter jet is moving through still air. On Neptune, the air itself is moving that fast, and the only things in it are clouds of frozen methane, ammonia ice crystals, and the occasional storm system the size of a continent. Voyager 2 photographed one of those storm systems during its flyby in August 1989. The probe arrived at Neptune after 12 years of travel, and the team on Earth had assumed, going in, that Neptune would be visually similar to Uranus. Uranus had been the previous target, and Uranus, when Voyager 2 photographed it 3 years earlier, was almost featureless. A pale blue-green ball, with no visible weather, no storms, no bands. The atmosphere of Uranus was, at the time, the dullest atmosphere of any major planet ever photographed close up. The expectation was that Neptune would be similar. It was not. When the first images came back from Voyager 2, the team saw a planet wearing a giant dark spot the size of Eurasia, embedded in a deep blue atmosphere streaked with white methane clouds, and surrounded by a system of broken rings that nobody on Earth had been able to see properly from a distance. The dark spot was a storm. The team named it the Great Dark Spot, by analogy with Jupiter's Great Red Spot. It was roughly 13,000 kilometers across, large enough to swallow Earth whole, and the winds at its edge were measured at over 2,000 kilometers per hour. The Great Dark Spot was photographed for several months. Then it disappeared. When the Hubble Space Telescope was pointed at Neptune in 1994, 5 years after Voyager 2's flyby, the dark spot was gone. There was a different one in a different place. By 2018, scientists had identified a third dark spot, again in a new location, and they were able to track its evolution and eventual decay. Neptune's storms appear and disappear on timescales of years. They do not last for centuries the way Jupiter's Great Red Spot does. They erupt, they spin, and they vanish. And during their lifespan, they are some of the most violent atmospheric phenomena ever observed in the solar system. Now think about what this means for any spacecraft trying to enter Neptune's atmosphere. On Mars, when a probe enters the atmosphere, the air is thin and the wind speeds are low. On Venus, the atmosphere is dense and corrosive, but at least it is relatively calm at the cloud levels we have probed. On Saturn, the Cassini probe ended its mission by diving into the atmosphere in 2017. The winds were strong, but the descent was brief and controlled, and the probe was never expected to survive past the upper layers anyway. On Neptune, any descent vehicle would be trying to push through air that is moving past it faster than the speed of sound, with internal energy enough to maintain that speed indefinitely, and storm systems that erupt and vanish without warning, sometimes the size of continents. The sheer forces alone would tear a probe apart before it reached any meaningful depth. And there's another problem, which is the thermal one. 2,000 km/h winds passing over a stationary object generate friction. Friction generates heat. Even in an atmosphere whose ambient temperature is 221 degrees below 0 Celsius, the friction of supersonic flow against a probe's hull would create localized heating intense enough to compromise structural materials. And we are not even at the descent yet. We are still talking about entering the upper atmosphere. There has been exactly one mission to Neptune, Voyager 2. It did not enter the atmosphere. It did not orbit. It performed a single flyby at a closest approach of about 4,950 kilometers above the cloud tops. And then it left. It used Neptune's gravity to bend its own trajectory southward, away from the plane of the solar system, and it has been moving in that direction ever since. Voyager 2 did not stay because Voyager 2 could not stay. The mission planners knew going in that they had one chance, one pass. Whatever data they could gather in those few hours of close approach was all the data we were going to get for at least a generation. It has now been 36 years. We have not gone back. Part of the reason is the wind. Part of the reason is everything below the wind. But the wind alone is enough to keep most descent missions, on paper, from ever leaving the proposal stage. And here is the part that should worry anyone who thinks this might be solvable in the near future. We still do not know exactly why the winds are this fast. The deep convection theory is the leading explanation, but it is not a solved problem. Without a complete model of what drives Neptune's atmosphere, we cannot predict what we would encounter inside it. And we cannot send a probe into a system we cannot model. On every other planet, we knew what the atmosphere would do before we entered it. On Neptune, we do not. The planet is moving faster than sound. In a darkness almost no light reaches, and we still cannot tell you where the energy is coming from. It is in the dark. We are guessing, and we have not even started descending yet. The engine inside the engine, I want to come back to the internal heat for a minute, because it is one of the most underrated facts about the outer solar system, and once you understand what it implies, the whole rest of this script changes shape. Neptune radiates 2.5 times more heat than it receives. Said another way, Of all the energy Neptune is throwing out into space, less than half of it came from the sun. The rest, more than half, came from inside the planet. What is sitting inside Neptune that produces that much heat? 4.5 billion years after the planet formed. Imagine you took a stove, turned it on, and then turned it off. The metal stays warm for a while. After an hour, it is still warm. After a day, it is room temperature. After a week, you would not know it had ever been hot. The thing about leftover heat from formation is that it leaks out. The bigger the object, the slower it leaks, but it always leaks. Earth still has some of its formation heat. Most of the heat at the center of our planet, though, comes from radioactive decay of elements like uranium and thorium and potassium in the mantle and crust. The decay is slow. It will continue for billions of years. That is why Earth's interior is still molten, even though our planet is the same age as Neptune. But Neptune does not have much rock and metal in its interior. It is not a rocky planet. It is what scientists now call an ice giant, mostly water and ammonia and methane, with a relatively small core. The composition does not allow for the same kind of radioactive heating that powers Earth's interior. So the formation heat theory has to do most of the work, and the formation heat theory has to explain why Neptune is still pumping out twice the energy of Uranus despite being a similar age and composition. It is a puzzle that has been open since at least 1989, and the puzzle deepens when you compare the two ice giants directly. Uranus and Neptune are sometimes called twins, and in size and mass and bulk composition, the comparison is fair. But Uranus radiates only 1.1 times the energy it receives from the Sun. Neptune radiates 2.61. Same age, same kind of planet, different internal engine. The leading theory for the difference involves Uranus's strange tilt. The planet is rotated almost 90 degrees relative to its orbit, and one common explanation is that it took a massive impact early in its history, possibly from a body the size of Earth, which knocked the planet sideways and may have stirred up its interior in a way that allowed its formation heat to escape much faster. If that is right, Uranus is not the twin. Uranus is the broken sibling, and Neptune is the planet behaving the way the family was supposed to behave, with all of its formation heat still locked inside, slowly leaking out into the dark. But here's the part that matters for our story. When you stand at the cloud tops of Neptune, you are standing on top of a heat source. The planet is not sitting in equilibrium with its environment. It is shedding energy, slowly, continuously, from the inside out, and that energy has to travel through every layer of the planet on its way to space. If you imagine Neptune as a series of nested shells, each shell is hotter than the one above it. The cloud tops are at 50 Kelvin. A few hundred kilometers down, you are at room temperature. A few thousand kilometers down, you are hotter than boiling water. By the time you reach the deep interior, you are at thousands of Kelvin, and the pressure is in the hundreds of gigapascals. This is not unusual for a planet. Earth has the same gradient in principle. The center of Earth is hotter than the surface. But on Earth, you can stand on the surface, and the surface is solid. And the only way to reach the deep interior is to drill. And we have never drilled more than about 12 kilometers down. On Neptune, there is no surface. There is only the gradient. The atmosphere blends into the deeper layers, and the deeper layers blend into the mantle, and the mantle blends into the core, and there is no point at which you can say, here is where the planet starts. The whole thing is the planet. The whole thing is the engine. Anything that descends into Neptune is descending into the engine itself, and the engine has been running for 4.5 billion years, without burning down, without cooling off, without slowing. This is the paradox at the heart of everything we are about to talk about. Neptune may be the cleanest one-way door in the outer solar system, and the reason it does not let go is because it is hot on the inside, in a way no one fully understands. The supersonic winds are powered by it. The diamond rain is forged by it. The superionic ice is held in place by it. The escape velocity is set by it. If you turned off the engine, the planet would simmer down over millions of years and become merely difficult to visit, instead of impossible. But the engine has not turned off. There is no sign that it will. And as long as it is running, the planet is doing things to matter that nothing else in the solar system does. We are about to look at the things it does, starting with the layer that has no surface. There is nothing to land on if you brought a lander to Neptune. Where would you land it? I want you to actually try to answer the question, because it sounds trivial, and it is not. On Mars, the answer is obvious. You pick a relatively flat plane. You bring an airshell. You parachute through the thin atmosphere. You fire a retro rocket, and you set down on basalt. On the Moon, even simpler. There is no atmosphere. You just decelerate and touch down on regolith. On Venus, harder, because of the heat and pressure, but still, there is a surface. Soviet probes landed on it in the 1970s and survived for an hour or two before the heat killed them. On Neptune, the question is wrong. Neptune is not a rocky planet covered in atmosphere. Neptune is atmosphere, all the way down, until the atmosphere becomes something else, and that something else becomes something else, and at no point in the descent do you encounter what we would normally call ground. The structure of the planet, as best we currently understand it, looks something like this. At the top, you have the visible cloud layer. This is what Voyager 2 photographed. Mostly hydrogen and helium with traces of methane, which is what gives the planet its blue color. Methane absorbs red light. The light that comes back to us is blue. That layer is several hundred kilometers thick. Beneath the visible clouds, the atmosphere thickens. Hydrogen and helium are still the main components. The pressure increases. The temperature increases. After 1,000 kilometers or so, the gas is no longer behaving like the gas you breathe on Earth. It is being compressed into something denser, something that starts to behave more like a fluid than a gas, with properties that do not exist on the surface of any rocky planet. Below that, somewhere, you reach the mantle. The mantle is mostly water, with ammonia and methane mixed in. It is sometimes called the icy mantle, but it is not ice in any familiar sense. The temperature is thousands of Kelvin. The pressure is hundreds of gigapascals. We will get to what water actually does at those conditions in a few sections, because it is one of the most extreme things we have ever recreated in a laboratory. For now, just know that the mantle is hot, dense, and roughly the consistency of something between hot taffy and hot syrup. Not solid, not exactly liquid, something in between, behaving in ways that nothing on Earth behaves. Below the mantle is the core. We think. We are not entirely sure. The core is probably rocky, probably about the size of Earth, possibly with some metallic content, sitting at the center of the planet under unimaginable pressure. We have never measured it directly. We have never imaged it. Our knowledge of Neptune's core comes entirely from indirect inference, from the planet's gravitational field, its rotation, its magnetic field, and our best models of how planets like this should form. So when you ask, where would you land a lander? The honest answer is, you cannot. There's no surface to land on. The atmosphere thickens gradually until it becomes the mantle. The mantle thickens gradually until it becomes the core. And at no point in the descent is there a clean transition where you could say, here, this is solid. This is where I stop falling. What this means, in practice, is that any vehicle entering Neptune's atmosphere is on a one-way trip. It enters the cloud layer. The pressure increases. Eventually the pressure exceeds whatever the vehicle was rated for, and the vehicle is crushed. Whether it makes it 10 kilometers down, or 100, or 1,000 is a question of engineering. But it is not a question of when it stops descending. It does not stop descending. It just stops existing. There is one mission profile that has been seriously studied for the outer giants. It is called an atmospheric probe mission, and the model is the Galileo probe, which dropped into Jupiter's atmosphere in 1995. The Galileo probe was a small instrument package that descended on a parachute, transmitted data back as long as it could, and then was crushed by the increasing pressure of Jupiter's atmosphere. It survived for about an hour and reached a depth where the pressure was about 23 times the atmospheric pressure at sea level on Earth. 23 bar. That was the limit on Jupiter, with mid-1990s engineering. Neptune is similar in profile, but the technological challenge is harder, because Neptune is much further away. Communication is harder, and we have less prior data to design against. A Neptune atmospheric probe, even with modern technology, would probably reach a similar depth before being destroyed. Maybe slightly deeper, maybe somewhat similar. Beyond that point, the spacecraft is gone. And here's the thing nobody tells you about probes like this. They are not designed to come back. They are not designed to survive. They are designed to fall into the atmosphere, transmit a few hours of data, and die. The mission is the descent. The transmission is the science. The probe is consumable. There's no version of a Neptune mission, with current technology or anything proposed in the next 30 years, that involves recovering anything from inside the atmosphere. Once you go in, you are gone. And the deeper you go, the worse it gets, because the things waiting in the deeper layers are not just pressure. They are diamond. They are superionic ice. They are temperatures approaching the surface of the sun. And they are sitting there, patiently, in the dark, 4.5 billion kilometers from the nearest star. We will get to them. But first, the crush layer. That is next. The pressure wall. Pressure is one of those words that humans have a terrible intuition for, because we live in a very narrow band of it. The atmospheric pressure at sea level, where almost all human beings live, is about 100,000 pascals, or 1 bar. That is the baseline. That is the only kind of pressure your body has ever known. If you climb to the top of Mount Everest, the pressure drops to about 1/3 of that. Climbers struggle to breathe. The body cannot get enough oxygen. People die at this pressure if they are not acclimated. And that is only a factor of 3 less than what you experience right now sitting still. If you go in the other direction, into the ocean, the pressure goes up. At 10 meters of depth, it doubles. At 100 meters, it is roughly 10 times the surface pressure. At the bottom of the Mariana Trench, the deepest point in the ocean, it is about 1,000 bar, or 100 megapascals. That is 1,000 times the pressure you live in. Things crush. Steel deforms. Water itself behaves strangely. And only specially engineered submersibles, of which there have been very few in human history, have ever gone down there and come back. Now I want you to forget the Mariana Trench, because Neptune makes the Mariana Trench look like a swimming pool. At the cloud tops of Neptune, where Voyager 2 took its photographs, the pressure is about 1 bar, roughly the same as sea level on Earth. You could, if you had the right thermal protection and a breathing apparatus, walk through the cloud tops without being crushed. But the cloud tops are also moving at 2,000 kilometers per hour, and the temperature is 221 degrees below zero. So let us not dwell on that. Now let us descend. After about 1,000 kilometers of descent, the pressure has climbed to several thousand bar. You are now in conditions worse than the bottom of the deepest ocean on Earth. The atmosphere is no longer behaving like air. It is dense, hot, and supercritical, which means it does not have a clear distinction between gas and liquid anymore. You are inside a fluid that has more in common with the mantle of a planet than the air of a sky. After several thousand kilometers, you are hundreds of thousands of bar, tens of gigapascals. This is the pressure regime in which water starts doing things that water does not do anywhere on Earth. The temperature is also rising into the thousands of Kelvin. You are now inside the icy mantle. By the time you reach the core of Neptune, the pressure is approximately 700 gigapascals, 7 million bar, 7 million times the pressure of the air you breathe right now. The temperature is about 5,400 Kelvin, nearly as hot as the surface of the sun. Imagine a temperature close to the sun's surface, sitting at the bottom of 7 million bar of pressure. That is the core of Neptune. There's no material in our current technological inventory that can survive these conditions intact. Diamond, the hardest material we have, deforms under similar pressures. Tungsten, our densest practical metal, would not maintain structural integrity. The strongest alloys we have ever fabricated would fail. Now I want to come back to the question of a probe descending through this. A spacecraft entering Neptune's atmosphere starts at 1 bar. It is rated for that. Then it descends. The pressure climbs. At 10 bar, the spacecraft is fine. At 100 bar, it is starting to flex. At 1,000 bar, the heat shield is failing. At 10,000 bar, the structure is collapsing. At 100,000 bar, there is nothing left of the spacecraft that you would recognize as a spacecraft. It has been compressed into a smear of compressed metal and ceramic, dispersing into the surrounding fluid, indistinguishable from the planet itself. And the pressure is still going up. By the time you reach the depths where the diamond rain begins, the spacecraft has been gone for hundreds of kilometers. By the time you reach the superionic ice, the spacecraft is no longer a discrete object. It is dissolved into the mantle. Its atoms are still there, somewhere. But as a probe, as a vehicle, as anything that could transmit information, it has ceased to exist. I want to be specific about something here, because I think it gets glossed over in pop science treatments of Neptune. The pressure does not just kill the probe. The pressure consumes the probe. Whatever the probe is made of, after a certain depth, becomes part of the planet. The carbon in the probe might end up in the diamond rain. The metals in the probe might sink toward the core. The hydrogen and helium displaced by the probe's entry simply mix back into the surrounding atmosphere, and within a few decades there is no trace, anywhere, that the probe ever existed. This is a fundamental difference between Neptune and Mars, or between Neptune and the Moon. On Mars, our probes are still there. The Viking landers from the 1970s are sitting on the surface, slowly being weathered by Martian dust storms, but recognizable. Curiosity is still rolling. Perseverance is still active. Every artifact we have ever sent to Mars is still on Mars, in some form. On Neptune, no artifact survives. None. There is nothing to be sent that comes back. There is nothing to be sent that even stays in one piece. When Voyager 2 passed Neptune in 1989, it did not go in. It flew over. It took photographs from above. Then it bent its trajectory and continued out into interstellar space. The reason is not that the team was being cautious. The reason is that there was no version of the mission where you would survive entry. None. Even with the hardened atmospheric probe, the data return would have been measured in hours at most, and then the probe would have been gone. And Voyager 2's gravity assist required something specific from Neptune, which we will get to in a few sections. The probe approached the planet from one specific angle, used its gravity to bend its course, and accelerated outward. Anything else, and Voyager 2 would have either fallen in, or been thrown into a different orbit entirely. The trajectory was a knife edge, and the planet was the blade. But before we get to Voyager 2, we have to talk about what is in the layer below the crush, because the next layer is where the planet starts doing something we did not even know was possible until 2017. The next layer rains diamond, and we have proof. The layer that rains diamond, I want to tell you about an experiment that took place at a laboratory in Menlo Park, California, in 2017. The laboratory is called the SLAC National Accelerator Laboratory. It sits in the hills above Stanford University. It hosts one of the world's most powerful X-ray lasers, an instrument called the LINAC Coherent Light Source. And on a particular set of days in 2017, a team of researchers, led by a former Lawrence Livermore scientist named Dominic Krauss, used that laser to do something nobody had ever done before. They created Neptune in a tabletop sample for a few billionths of a second, and watched what happened. What they saw was diamond rain. Let me back up and explain what that means, because it is one of the more genuinely strange facts about ice giants, and it has only recently been confirmed. The atmosphere of Neptune is rich in methane. Methane is a simple molecule, one carbon atom bonded to 4 hydrogen atoms. It is what gives the planet its blue color. As you descend through Neptune's atmosphere, the methane is subjected to increasing pressure and temperature. At a certain depth, the conditions become extreme enough that the methane molecules can no longer hold themselves together. The carbon-hydrogen bonds break. The hydrogen drifts away. The carbon is left. And the carbon, under the pressure and temperature found at that depth in Neptune, has only one stable form. It crystallizes into diamond. This was first proposed as a theoretical possibility in the 1970s and 1980s. It made physical sense. The conditions at the right depth in Neptune, between roughly 5,000 and 10,000 kilometers below the cloud tops, are similar to the conditions at which we synthesize diamond on Earth in industrial labs. The chemistry checks out. The physics checks out. But it was a theoretical prediction. We had no way to confirm it. The conditions could not be reproduced on Earth. The equipment did not exist. Until 2017, the team at SLAC took samples of polystyrene, which is a plastic with a chemical formula that mimics methane and the hydrocarbon mix in Neptune's atmosphere. They placed the samples in front of an intense optical laser, which generated shock waves that compressed and heated the plastic to conditions matching the deep interior of Neptune. While that compression was happening, they used the X-ray laser to take pictures of the molecular structure of the sample at speeds measured in femtoseconds. quadrillionths of a second. What they saw was the carbon in the plastic separating from the hydrogen and crystallizing into diamond. In real time. Tiny diamonds, only a few nanometers across, but diamonds. Real diamond, with the same crystal structure as a wedding ring, formed in the laboratory under conditions that exist nowhere on Earth except inside that laser pulse. The experiment was published in Nature Astronomy. It was the first direct experimental confirmation that diamond rain happens. Not a theory, not a model, an observation, a measurement, and it has implications. Inside Neptune, somewhere between 5,000 and 10,000 kilometers below the cloud tops, the methane in the atmosphere is being broken apart. The carbon is being pressed into diamond, and the diamond is sinking. Diamond is denser than the surrounding atmosphere, so it falls. It falls through the supercritical fluid, through the mantle, possibly all the way to the core. There is, by some estimates, an entire layer of Neptune that is essentially a slow rain of diamond particles, falling toward the deep interior, accumulating around the core like sediment around an underwater mountain. The particles are small. Most of them are probably no larger than a grain of sand, but over the 4.5 billion years that Neptune has existed, the cumulative mass of diamond at the bottom of that rain is potentially enormous. We do not have a precise number, because we have not measured it directly, but the order of magnitude calculations suggest that there could be hundreds of tons of diamond falling toward Neptune's core every year, and that this has been happening continuously since the planet formed. Try to picture that. A planet whose interior contains, possibly, the largest diamond reservoir in the solar system, buried under thousands of kilometers of supersonic atmosphere and superionic ice, at temperatures approaching the surface of the sun, in pressures that no spacecraft can survive. And before you start thinking about mining missions, let me destroy that idea quickly. To extract diamond from Neptune, you would need to descend to the layer where it forms, gather the particles, and lift them back to orbit. The first part requires technology that does not exist. The second part requires fighting the supersonic winds, the crush pressure, and Neptune's escape velocity, which we will get to in a few sections, and which is 23.5 kilometers per second. There is no rocket on Earth that can be brought to Neptune, fueled, and used to lift several tons of payload from the deep interior to escape velocity. There's no plausible engineering proposal that gets us there. There's no realistic technology pathway in the next century. The diamonds will stay where they are. The reason this matters for our story is not the diamond itself, but what its existence tells us about the planet. The diamond rain is a signature. It tells you that Neptune is not just sitting there being cold. It is actively transforming the matter inside it. Methane is being broken down. Carbon is being crystallized. Hydrogen is being released. There are chemical processes happening all the time, throughout the planet, that exist nowhere else in our solar neighborhood. Saturn has been rumored to have similar processes. Jupiter similar. But on Neptune, the depth profile and the chemistry are such that the diamond rain layer is more extensive, more stable, and more diagnostically clear than on the other giants. The 2017 SLAC experiment was specifically designed to mimic Neptune's conditions. And there's one more piece of this story, which I want to mention, because it has only been confirmed in the last few years. In 2022, a follow-up team published results indicating that the diamonds inside ice giants like Neptune may not just be falling. They may be growing. The conditions in the deeper interior are right for diamonds to continue accreting carbon as they fall, getting larger as they sink. The diamonds at the top of the rain layer might be nanometers across. The diamonds at the bottom, by the time they reach the core, might be much larger. We do not know how large. The current models suggest that some of them could be the size of icebergs, diamond icebergs, falling toward the core of a planet 4.5 billion kilometers from the sun, in a darkness that will never end, in a temperature higher than the surface of our star. It is one of the most extreme things we have ever proposed to be physically real, and the evidence keeps accumulating that it is. And it is not even the strangest thing about Neptune's interior. The strangest thing is the layer below the diamond, the layer where water itself does something scientists predicted decades ago, but only confirmed in the laboratory recently. That is next. The water that conducts electricity. Water is one of the most studied substances in the history of science. We know it cold, hot, frozen, boiling, vaporized, supercritical, ionized. We have cataloged at least 17 different crystalline phases of ice, each with a different molecular structure, each occurring at a different range of pressures and temperatures. And in 1988, a theoretical physicist proposed that there should be one more phase, a phase that nobody had ever observed, a phase that exists only under conditions found nowhere on Earth, at pressures of hundreds of gigapascals and temperatures of thousands of Kelvin. The physicist predicted that water in this regime would do something genuinely strange. The oxygen atoms would lock into a crystalline lattice, like a solid, but the hydrogen atoms would break free of their bonds and move around inside the lattice, like a liquid. The result would be a substance that is solid and liquid at the same time, depending on which kind of atom you were looking at. This phase was called superionic ice. For 30 years, it was just a theoretical prediction. Computer simulations supported it. The math worked. But no laboratory on Earth could create the conditions needed to verify it. The pressures were too high. The temperatures were too high. The technology did not exist. Until 2018. In February 2018, a team of researchers at Lawrence Livermore National Laboratory, working with collaborators at UC Berkeley and the University of Rochester, published a paper in Nature Physics. They had used high-powered lasers to compress water samples to hundreds of gigapascals while simultaneously heating them to thousands of Kelvin for the brief moments before the sample vaporized. And in that brief moment, they had observed it. Superionic ice. The phase that had been predicted 30 years earlier was real. And they confirmed something else. Something that mattered for our story. Superionic ice almost certainly exists, in vast quantities, inside Neptune. Let me explain what that means. Neptune is composed, by mass, mostly of water and ammonia and methane. The water makes up something close to 65% of the planet's interior mass. Most of that water sits in the mantle, at depths where the pressure is in the hundreds of gigapascals and the temperature is in the thousands of Kelvin. Those are exactly the conditions where superionic ice forms. So somewhere inside Neptune, between the diamond rain layer above and the rocky core below, there's a vast region, possibly thousands of kilometers thick, made of water that is half solid and half liquid. The oxygen atoms are locked in a crystal lattice. The hydrogen atoms are flowing through the lattice like a fluid. The mass behaves like a solid mantle, the kind of mantle that supports the convection patterns that generate planetary magnetic fields. And the loose hydrogen ions, flowing through the lattice, conduct electricity. This last part matters more than it sounds, because it solves a long-standing puzzle about Neptune's magnetic field. Neptune has a magnetic field. So does Uranus. And both fields, when they were measured by Voyager 2 in the 1980s, did something nobody expected. They were tilted, severely tilted. Earth's magnetic field is roughly aligned with Earth's rotational axis, off by about 11 degrees. Jupiter's and Saturn's are similarly aligned. But Uranus's magnetic field is tilted by about 60 degrees relative to its rotation, and it is also offset, meaning the magnetic dipole is not centered on the planet at all. Neptune's is similar, about 47 degrees of tilt, and a significant offset. For decades, this was unexplained. Standard models of planetary magnetic fields assume that the field is generated by a fluid, electrically conducting layer near the planet's center, surrounded by less conductive material above and below, like a churning bath of molten iron at the heart of the planet. That model produces a centered, aligned field. Earth, Jupiter, Saturn, all explained. Uranus and Neptune, not explained. But if you assume that the conducting layer is not a deep iron core, and is instead a shallow shell of superionic ice, surrounded by both a normal fluid layer above and a more solid mantle below, then you can produce a tilted, offset magnetic field. The geometry is right. The physics is right. The 2018 LLNL experiment, by demonstrating that superionic ice is real, gave the thin-shell dynamo theory a foundation it did not have before. So Neptune's magnetic field, the strange tilted offset thing nobody understood for 30 years, is being generated by a layer of water that conducts electricity, sitting halfway between the cloud tops and the core, doing something that no other substance in the universe is known to do. And here is where the experiment becomes more important than just confirming a phase of matter. When the LLNL team published their results, They did not just announce the existence of superionic ice. They announced that this phase of matter is potentially the most abundant solid in the universe. Not on Earth, where we never see it, but out there, in the interiors of every ice giant, every mini Neptune, every water-rich exoplanet ever discovered. Neptune is the closest example. There are countless others. The Kepler telescope and its successors have found, in the years since 2009, that the most common type of planet in our galaxy is something called a sub-Neptune, or a mini-Neptune, a planet smaller than Neptune but bigger than Earth, made mostly of water and rocky core, with a thick atmosphere of hydrogen and helium. There are billions of them, possibly trillions. They are the dominant planet type by far, and every single one of them, if it follows Neptune's profile, has a layer of superionic ice in its interior. The most common solid in the universe is something we did not even know existed in 2017, and we cannot reach it. We cannot extract it. We cannot study it directly. We cannot send a probe to Neptune to measure the superionic ice in situ, because the probe would be destroyed long before it reached that depth, and even if it survived, the data could not be transmitted out, because the planet's magnetic field and the 4-hour communication delay would interfere. Everything we know about superionic ice, we know from a brief flash inside a laser chamber in California, and from theoretical models calibrated against that flash. It is one of the strangest features of modern planetary science. The most common solid in the universe, the substance that builds the interiors of more planets than anything else, is something we have only ever observed for a few billionths of a second, in a single laboratory on Earth. Outside of that lab, it sits inside Neptune, in a layer of unknown thickness, conducting electricity, generating a magnetic field that does not align with anything else in the solar system, holding the planet's magnetic geometry in a configuration that nothing else can explain. And we have not been back since 1989. And we are not going, because the next problem is escape velocity. And escape velocity, on Neptune, is the wall everything else is built on. That is next. The velocity you cannot reach from inside every planet has an escape velocity. It is the minimum speed at which an object has to be moving away from the surface in order to permanently leave the planet's gravity. If you are slower than escape velocity, you fall back. If you are faster, you keep going. On Earth, escape velocity is 11.2 kilometers per second, about 40,000 kilometers per hour. That is what a rocket has to achieve, ultimately, to leave Earth and never come back. It is why rockets are so big. Most of the rocket is fuel. The fuel exists to push the small payload at the top up to that speed. On the Moon, escape velocity is much lower, only about 2.4 kilometers per second, which is why the Apollo lunar modules were small. They did not need to carry as much fuel to leave. On Mars, it is 5 kilometers per second, higher than the Moon, lower than Earth. Manageable with current technology. The Mars Sample Return mission, when it eventually launches, will need to lift its sample container to about that speed to send it home. Now let us look at Neptune. Neptune's escape velocity, at the cloud tops, is 23.5 kilometers per second. That is more than twice Earth's. It is more than 4 times Mars's. It is roughly 10 times the Moon's. But here is the part most people get wrong. The 23.5 kilometers per second is only the clean number at the cloud tops. From orbit, looking down on paper, inside the atmosphere, the real problem becomes worse than escape velocity. Drag, pressure, no launch platform, and a rocket equation that collapses before it begins. Let me unpack what that means, because each of those words is doing a lot of work. Start with drag. Neptune's upper atmosphere is dense enough and moving fast enough that any rocket trying to climb through it would be fighting two things at once. The atmospheric resistance itself, slowing the rocket as it pushes upward, and the relative motion of the air, which is moving at 2,000 kilometers per hour. A rocket trying to ascend through that is not just fighting gravity. It is fighting a sustained crosswind faster than the speed of sound. Every meter of altitude gained costs extra fuel against the drag. The losses are not small. On Earth, drag losses during ascent are typically a few hundred meters per second of delta V. On Neptune, the equivalent losses would be measured in kilometers per second. Then there is pressure. Below the cloud tops, the pressure climbs fast. Within a few hundred kilometers of descent, the rocket is in conditions that would compromise its structural integrity, its fuel tanks, and its engines. Even if you wanted to launch from a deeper layer, the rocket itself could not survive being there. Then there is the launch platform. There is none. Anywhere. At any depth. There is no surface to set up a launch pad on. No solid ground to ignite engines against. Rockets work by pushing exhaust against something, and that something has to be solid enough to provide a reaction. Liquid pressure provides resistance, but not the kind of stable foundation a launch needs. A rocket trying to lift off from a fluid medium that is itself in turbulent supersonic motion has problems no engineer has ever solved on Earth. And finally, the rocket equation. The basic math of rocketry says that to reach a given delta V, you need a mass ratio of fuel to payload that grows exponentially with the delta V required. To leave Earth, you need a mass ratio of about 30 to 1. To leave Neptune, even from the cloud tops, with no atmospheric losses, you would need a ratio that is dramatically higher. Add the drag losses, add the pressure constraints, add the lack of a launch platform, and the mass ratio you would need to lift even a small payload from inside Neptune's atmosphere becomes physically impossible. The fuel itself would weigh more than what any rocket could carry. In practical terms, this means that any vehicle that descends into Neptune's atmosphere is committed to staying there. There's no fuel mass you could bring with you into Neptune's interior. That would close the energy budget for a return trip. The math does not work. The chemistry does not work. The engineering does not work. The only realistic mission profile to Neptune today is a flyby or an orbiter. A flyby is what Voyager 2 did. The probe approached the planet, took photographs and data for a few hours, and continued on. An orbiter would arrive, slowed down enough to get captured by Neptune's gravity, and circle the planet for years, sending data back. Neither mission goes inside the atmosphere. Neither mission comes back with anything physical. And here is where Voyager 2's trajectory becomes a kind of warning, rather than an inspiration. Voyager 2 used Neptune's gravity, very specifically, to bend its own trajectory southward. The mission planners knew going in that there was no way to insert into Neptune orbit. The probe was moving too fast. The fuel was running out. The only options were a flyby that bent the probe one way, or a flyby that bent the probe another way. They chose the way that would also send the probe past Triton, Neptune's largest moon, on the way out. After the Triton flyby, Voyager 2 continued on its trajectory, southward, out of the plane of the solar system, into interstellar space, where it remains today. It is currently more than 130 astronomical units from Earth, moving at 15.4 kilometers per second, heading toward the constellation Telescopium, in a direction nothing else has ever traveled. It will never come back, not because we lost it, because Neptune set its course, and the course goes outward, and there is nothing in front of it for thousands of years. The next star Voyager 2 will pass within a few light years of is 40,000 years from now. This is the real lesson of escape velocity at Neptune. It is not just that you cannot land and take off. It is that the planet itself, when you visit it, dictates where you go next. You arrive on its terms. You leave on its terms. And the terms include a permanent exile. Voyager 2 is the only spacecraft that has ever reached Neptune. It is also the only spacecraft that will not come home. The two facts are connected, and they are connected by physics, not policy. The probe that could not come home, I want to spend a section on Voyager 2 by itself, because the story of the Neptune flyby is one of the most extraordinary things that humans have ever done, and most people do not know it happened. Voyager 2 launched on August 20th, 1977. It launched from Cape Canaveral on a Titan I Centaur rocket, 16 days before its twin Voyager 1, which would take a different route. The mission was originally planned to be a study of Jupiter and Saturn. The mission was funded for about 5 years. The probe was built to last that long. It is now 48 years old. It is still operational. It is the only spacecraft that has ever visited Uranus or Neptune. The journey to Neptune took 12 years. Voyager 2 visited Jupiter in 1979. It visited Saturn in 1981. It visited Uranus in 1986. And on August 25, 1989, 12 years and 5 days after launch, It made its closest approach to Neptune. The probe passed about 4,950 kilometers above the cloud tops of Neptune's North Pole. 5 hours later, it passed about 40,000 kilometers from Triton, Neptune's largest moon. And then it left. The data that Voyager 2 collected during those few hours represents, almost in its entirety, everything humanity knows about Neptune from direct close-range observation. Every image, every measurement, every confirmed feature of the planet's atmosphere, magnetic field, ring system, and moons. All of it was acquired in roughly 12 hours of close approach by a single spacecraft, 36 years ago. We have not been back. Nothing has gone in Voyager 2's place. Everything we have learned about Neptune since 1989 has come from Hubble, from ground-based telescopes, from the James Webb Space Telescope after 2022, and from theoretical models. All long-range observations, none of them up close. The team that ran the Voyager 2 Neptune flyby knew, going in, that they had one chance. They knew the mission was a one-way encounter. They knew the probe would not enter orbit. They knew there would be no follow-up mission for at least a generation. And they planned every detail of the encounter, the pointing of every instrument, the timing of every data transmission, with the understanding that whatever they could not measure during those 12 hours of approach was lost forever. And they did extraordinary work. Voyager 2 discovered 5 moons of Neptune that had not been seen from Earth. It confirmed the existence of Neptune's ring system, which had been suspected from earlier ground-based observations, but never confirmed. It mapped the Great Dark Spot. It measured the supersonic winds. It detected the magnetic field tilt. It photographed Triton up close for the first time, revealing a surface unlike anything else in the solar system, with active geysers, frozen nitrogen plains, and a temperature of negative 235 degrees Celsius. The Triton flyby, in particular, was a gift. The mission planners had a choice. They could send Voyager 2 past Neptune in one of two ways. One way would send the probe past Triton at close range, but at the cost of bending its trajectory steeply south, out of the plane of the solar system, where no other observations could be made. The other way would keep the probe roughly in the ecliptic, but Triton would be out of reach. They chose Triton. They chose the close encounter with the moon, knowing that it would commit Voyager 2 to a southward exit trajectory and an interstellar path that would take it forever away from anything else humanity might want to look at. It was the right call. The Triton flyby produced some of the most surprising data of the entire Voyager mission. The geysers on Triton, erupting nitrogen ice into the thin atmosphere, were a phenomenon nobody had predicted. Triton's surface was younger than expected, suggesting active resurfacing. The retrograde orbit, which we will get to in a section, was confirmed in detail, but the cost was that Voyager 2 went south. It bent its course downward through the ecliptic, accelerated outward, and is now traveling at about 15.4 kilometers per second relative to the Sun, heading toward the constellation Telescopium in the southern celestial sphere. It will never come back. And here is what I want you to feel about this, because I think it gets glossed over. Voyager 2 is not lost. Voyager 2 is not malfunctioning. Voyager 2 is not running out of power, although the radioisotope thermoelectric generator that powers it is slowly winding down, and within the next 10 years, the probe will go silent. Until then, it transmits data once a day from interstellar space, more than 130 astronomical units from Earth. The signal takes more than 19 hours, one way, to reach us. The probe is doing its job. The probe is healthy, but it is going one direction, outward, and the direction was set by Neptune. When the engineers planned the Neptune encounter, they understood that this was the trade-off. The price of seeing Neptune up close was that the probe would be sent on an exit trajectory, away from the rest of the solar system, into a region where nothing else could be observed. The price was the probe's future. The probe gave its future to see Neptune, and it could not have come back. Not by any version of the mission, not by any extension of fuel, not by any clever engineering. Once Voyager 2 left Earth in 1977, the trajectory was set. Once it passed Saturn in 1981, the trajectory was set even harder. By the time it reached Uranus in 1986, the trajectory was a knife edge, and Neptune was the final commitment. After Neptune, Voyager 2 had no fuel to course correct. The hydrazine in its tanks was reserved only for attitude control, for keeping its antenna pointed at Earth. Even today, almost 40 years later, that hydrazine is enough only to maintain orientation, not to change course. There is no spare energy. There is no maneuver. Voyager 2 is the only spacecraft that has ever visited Neptune. Voyager 2 is on a one-way trip out of the solar system. These two facts are not coincidence. They are the same fact. Anything that visits Neptune leaves on Neptune's terms. The geometry of the gravity assist, the energy of the trajectory, the placement of the planet at the end of the solar system, all of it conspires the same way. You arrive. You take what you can. And then the planet sets your course, and the course is outward, and the outward direction never bends back. It has been 36 years. We have not gone back, and there is no probe currently on its way. The next part of the story is the moon that Voyager 2 chose to see, because the moon is, in many ways, even stranger than the planet itself, and the moon is the final piece of the puzzle that explains why this whole system, planet and all, is a one-way capture zone. That is next. The moon that orbits backwards Triton is the largest moon of Neptune. It is the seventh largest moon in the solar system. It is roughly 2,700 kilometers in diameter, slightly smaller than our own moon, slightly larger than Pluto. It is one of only a handful of solar system bodies known to have a thin atmosphere of nitrogen, and it does something no other large moon in the solar system does. It orbits its parent planet backwards. Let me explain why this is strange. Almost every moon you can name, around almost every planet, orbits in the same direction that the planet rotates. The moon goes around Earth in the same direction Earth turns. The Galilean moons of Jupiter go around Jupiter in the same direction Jupiter turns. The major moons of Saturn, the same. Uranus, the same, even though Uranus is tilted on its side. There's a reason for this. When a planet forms, it does so out of a disk of dust and gas surrounding the young sun. The disk is rotating in one direction. As the planet condenses, it captures gas and dust from the disk, and the leftover material near the planet forms its own smaller disk, which condenses into moons. Those moons inherit the rotational direction of the disk, which inherited it from the parent disk. So everything spins the same way. Triton does not. Triton orbits Neptune in the opposite direction from Neptune's rotation. This is called a retrograde orbit, and the only viable explanation for it is that Triton did not form alongside Neptune. Triton formed somewhere else, was floating freely as an object in the outer solar system, and at some point, billions of years ago, it came too close to Neptune, and Neptune captured it. This is one of the most important facts about Triton, and it is also one of the most important facts about the Neptune system as a whole. Because Triton's capture is not a small event. Triton is large. The capture would have been violent. Most of Neptune's other moons, smaller and irregular, are now thought to be the result of disrupted earlier moons that were thrown into chaotic orbits by Triton's arrival. Triton came in. Triton stayed. And here is the other thing about Triton's orbit. It is decaying. Tidal forces between Triton and Neptune are slowly lowering Triton's orbit, pulling it closer to the planet, very slowly. In about 3 billion years, the orbit will reach what astronomers call the Roche limit, the distance at which Neptune's gravity will overpower Triton's own gravity, and Triton will be torn apart. The fragments will form a ring system around Neptune, larger and brighter than Saturn's. Triton is not just trapped. Triton is being slowly consumed. Now think about what this means for the system as a whole. Neptune captured a major moon billions of years ago. The moon's orbit is decaying. The moon will eventually be destroyed. And while it exists, it sits in a retrograde orbit, opposite to the direction the planet rotates, doing nothing else than the solar system does. This is the first sign that Neptune is not just a planet. Neptune is an attractor. Things come into the Neptune system. They do not come out. Voyager 2 photographed Triton in 1989. The photographs revealed a moon that nobody had expected. Triton's surface temperature is approximately negative 235 degrees Celsius. That is 38 Kelvin. It is one of the coldest places ever measured in the solar system. Colder than Pluto. Colder than most of the surfaces beyond the asteroid belt. And it is geologically active. Voyager 2 spotted geysers on Triton. Active eruptions of nitrogen gas. throwing material up to 8 kilometers above the surface. On a moon that cold, in a place that distant, in a body that small, geological activity should not be happening. There should not be enough internal heat to drive any active processes. Triton should be dead, frozen, inert. It was not. The geysers were a surprise, and they have been studied ever since. The leading theory is that solar radiation, even at the low intensity that reaches Triton, is enough to warm thin layers of nitrogen ice just below the surface, which then sublimate into gas and erupt through cracks. It is solar energy, amplified by the moon's own ice composition, producing visible geological activity in a place that should be in deep freeze. And there is a second source of internal heat, tidal flexing. As Triton orbits Neptune, the tidal forces between them stretch and squeeze the moon, generating internal friction, which produces heat. Not much, but enough, possibly, to maintain a subsurface ocean of liquid water beneath the icy crust. If there is a subsurface ocean on Triton, it joins the small list of solar system bodies where liquid water is suspected to exist. Europa around Jupiter, Enceladus around Saturn, possibly Titan around Saturn, possibly Pluto, and Triton around Neptune, in retrograde orbit, in a system humanity has visited exactly once. If life exists in any of those subsurface oceans, Triton is one of the candidates. We do not know. We cannot test. We have no way to send a probe. The closest we have ever come to studying Triton is Voyager 2's flyby in 1989. The probe passed Triton at a distance of about 40,000 kilometers, took photographs, took measurements, and continued on its trajectory out of the solar system. The data has been analyzed and reanalyzed for 36 years. Every plausible mission concept since 1989 has involved a flyby or a brief orbit. None has involved a lander. None has involved sample return. Triton is too far, too cold, and too embedded in the Neptune system, which is itself too far, too cold, and too dangerous for any current or near-future mission. There was a proposal called Trident in the early 2020s. It was a NASA Discovery-class proposal for a low-cost flyby of Triton. It was studied seriously. It made it through several rounds of evaluation. And then, in 2021, it was passed over for funding. Other missions were selected instead. Triton has not been revived. There was another concept called Neptune Odyssey, an orbiter mission that would arrive at Neptune in the 2040s and study the system for years. It was proposed in the most recent Planetary Science Decadal Survey. It was rated as a high priority for the next decade. It has not yet been funded, so the moon that orbits backwards, around the planet that does not let go, in the system humanity has visited exactly once, remains where it has always been, locked in retrograde, slowly falling, with geysers erupting through its frozen surface, in a darkness that no instrument is likely to see again in the lifetime of anyone listening to this. Triton is the marker. Triton is the proof. Triton is the moon that came from somewhere else, was captured, and could never leave. Like everything else that has ever entered the Neptune system, the 4-hour silence, imagine, for a moment, that we did somehow send a probe to Neptune. The fuel exists. The shielding works. The descent is planned. The probe enters the atmosphere, transmits data, and something goes wrong. On Earth, when a probe gets in trouble, the team sends commands. The Mars rovers have done this hundreds of times. Curiosity gets stuck on a sand dune, and within an hour, Mission Control sends a new set of instructions. Perseverance encounters an unexpected rock, and the team adjusts. Real-time decision-making, with delays of only a few minutes, allows missions to recover from problems and continue. On Neptune, this does not work. The one-way light travel time from Earth to Neptune, depending on where the two planets are in their orbits, ranges from about 4 hours to about 4.3 hours. That is the minimum. That is the speed of light. There is no faster way to send a signal. So when something goes wrong on a Neptune probe, here is what happens. The probe encounters the problem at, let us say, 12 noon Universal Time. The probe immediately transmits a distress signal. The signal travels at the speed of light, through the solar system, toward Earth. It arrives at Deep Space Network antennas at 4 in the afternoon. Engineers see the data, analyze it, identify the problem, and prepare a response. Best case, the response is ready by, say, 6 in the evening. They transmit it. The signal travels back through the solar system, again at the speed of light. It reaches the probe at 10 at night. Total elapsed time, 10 hours. But the probe was descending into Neptune's atmosphere when the problem occurred. In 10 hours, the probe is no longer where it was. It has either crashed deeper, or been blown off course by the supersonic winds, or been crushed by the increasing pressure. The response, when it arrives, is responding to a situation that no longer exists. The probe might already be destroyed. This is not a hypothetical. This is the standard problem with deep space missions to the outer planets. The Galileo probe at Jupiter operated almost entirely autonomously, because real-time control was impossible. The Cassini probe at Saturn, the same. Voyager 2 itself, during the Neptune flyby, executed a sequence of pre-programmed commands, with no real-time intervention possible, because the round-trip light time was over 8 hours. Any mission to Neptune today would face the same constraint, only worse, because the missions we would want to send are more ambitious than Voyager 2's flyby. We want orbital insertion. We want atmospheric entry. We want surface or near-surface measurements at Triton. All of these require precise, time-critical maneuvers that have to be planned in advance, with no possibility of correction in flight. If something goes wrong, you do not respond. You watch, and by the time you can respond, the mission may be over. There is one more dimension to this, which is the cost of failure. A Mars mission that fails costs hundreds of millions of dollars and a few years of work. A team can iterate. The next mission goes up in 2 or 3 years. A Neptune mission, with current technology, takes more than a decade just to arrive. The Voyager 2 trip took 12 years. A modern mission, depending on the launch window and the propulsion technology, might take 8 to 15 years. If the mission fails on arrival, you have lost more than a decade of work, several $billion, and the only Neptune flyby opportunity you might have had for another 20 or 30 years. This is one of the reasons missions to Neptune are so rare. Not because they are impossible, but because the cost of failure is enormous. The time to mission is decades, and the communication delay makes recovery from in-flight problems essentially impossible. It is one of the reasons no probe is currently on its way. It is also one of the reasons the proposals that have been submitted, like Trident and Neptune Odyssey, have struggled to compete with missions that go to closer targets, where failure can be recovered from, and success can be measured in years rather than decades. Neptune asks for too much. The distance, the gravity, the atmosphere, the moons, the magnetic field, the diamond rain, the superionic ice, all of it. And on top of everything, it asks for 4 hours of silence between every question and every answer. If you go to Neptune, you go alone, and the planet does not negotiate. The silence that has lasted 36 years. When was the last time a spacecraft visited Neptune? August 25, 1989. That was when Voyager 2 made its closest approach. After Voyager 2 left, no other probe has ever traveled to Neptune. Nothing has been launched. Nothing is currently in flight. That is 36 years. 36 years since any human-made object has come within close range of the 8th planet. To put that in context, when Voyager 2 reached Neptune, the World Wide Web did not exist. The Soviet Union still existed. Nobody had cell phones. The first iPhone was 18 years away. Most of the people listening to this video had not been born yet. Since 1989, humanity has sent probes to nearly every other major body in the solar system. Mars has had dozens of missions, including multiple rovers and landers. Venus has had a series of orbiters from various nations. Jupiter has had Galileo and Juno, with Europa Clipper now on its way, and Jupiter Icy Moons Explorer launched in 2023. Saturn had Cassini, which spent 13 years studying the system before deliberately diving into the planet in 2017. Mercury has had Messenger and Bepi Colombo. The Moon has had a renaissance of robotic missions. Even Pluto, much smaller and more distant, was visited by New Horizons in 2015. Neptune, nothing. And it is not because there has been no interest. There have been multiple proposals over the past 3 decades. Some made it through preliminary review. Some were studied in detail. None has been funded. Trident, the most recent serious proposal, was a NASA Discovery-class mission that would have flown by Triton in the late 2030s. It went through extensive concept development. It was a finalist in the most recent Discovery selection round. It was beaten out for funding by other missions. It was not selected, and there has been no follow-up. Neptune Odyssey was a more ambitious proposal, an orbiter that would have arrived at Neptune in the early 2040s and spent years studying the planet, its rings, and its moons. It was rated as a high priority in the most recent Planetary Science Decadal Survey, the document that NASA uses to plan its long-range mission portfolio. It has not been funded. The Decadal Survey recommendations are not commitments. They are aspirations. The funding has to come separately. There are also concepts in Europe and elsewhere. ESA, the European Space Agency, has studied ice giant missions. JAXA, the Japanese Space Agency, has expressed interest. China has discussed long-range outer planet missions in its strategic planning documents. None of them is on the launch pad. None of them is under construction. None of them is currently funded. The reason is not lack of interest. The reason is the cost. A flagship mission to Neptune, with current technology, would cost something like $2 to $4 billion and would take at least 10 years from launch to arrival. The cost is high because the distance is large, the launch energy is huge, the spacecraft has to be hardened against decades of radiation and cosmic ray exposure, and the mission has to be capable of operating autonomously for at least a decade with no possibility of repair or service. And the spacecraft has to carry its own power source, because solar panels do not work effectively at Neptune. The intensity of sunlight is too low. Any Neptune mission requires a radioisotope thermoelectric generator, like Voyager 2's, like Cassini's, like New Horizons. These power sources use plutonium-238, which is an extremely limited supply globally, and is reserved for high-priority deep space missions. The combination of high cost, long timeline, autonomous operations, plutonium fuel, and uncertain scientific return has kept Neptune at the back of the line. Meanwhile, the planet sits there, doing what it has been doing for 4.5 billion years, spinning at supersonic speeds, heating itself from inside, forging diamonds in its mantle, conducting electricity in its superionic shell, holding Triton in retrograde orbit, generating a magnetic field that nothing else in the solar system can match. And we have not been there since 1989. I want to be honest about something here, because I think this is one of the most under-recognized aspects of modern space exploration. There is a generation of planetary scientists alive today who were children when Voyager 2 reached Neptune. They watched the photographs come down on television. They read the early papers in school. They became scientists, in part, because of the wonder of those images. And they have spent their entire careers waiting for a follow-up mission that has never come. Most of those scientists will retire before another spacecraft visits Neptune. Some of them have already passed away. The next generation is now in graduate school, doing PhDs on Neptune topics, building careers around modeling and remote observation, knowing that the data they have to work with comes from a probe that flew by the planet decades ago, when their professors were still students. If a mission launched tomorrow, it would not arrive until at least the late 2030s. If it launched in 2030, it would arrive in the 2040s. If it launched in 2040, the 2050s. Most of us listening to this video may never see another close-up image of Neptune in our lifetimes. The planet is silent. We have made it silent, not by choice exactly, but by the slow accumulation of decisions, year after year, to fund other things, to prioritize other targets, to defer the eighth planet to a future that has not arrived yet. 36 years, and counting, and the planet does not care. The most common planet in the galaxy. I want to end with something that the last 20 years of exoplanet discovery have made impossible to ignore. Neptune is not a freak. Neptune is not unusual. Neptune is, by far, the most common kind of planet in the galaxy. Let me explain. When the Kepler Space Telescope launched in 2009, it began surveying a small patch of sky for planets orbiting other stars. By the time it ended its mission in 2018, it had confirmed more than 2,500 exoplanets and identified candidates for thousands more. Other telescopes, before and since, have added to the catalog. We now know of over 5,000 confirmed planets outside our solar system. And the most common type of planet in that catalog is something the astronomers call a sub-Neptune, or, sometimes, a mini-Neptune. It is a planet smaller than Neptune, larger than Earth, with a thick atmosphere of hydrogen and helium surrounding a rocky or icy core. Most of them have masses between 2 and 10 times that of Earth. Most of them have radii between 1.5 and 4 times that of Earth. There are billions of them, just in our galaxy. Sub-Neptunes do not exist in our solar system. There is nothing in the gap between Earth, at 1 Earth radius, and Neptune, at 4 Earth radii. We have a rocky planet, then nothing, then an ice giant. The space in between, where the most common planet type in the universe lives, is empty around our Sun. But around other stars, that gap is the densest occupied region of all. Sub-Neptunes are everywhere. They are the dominant planet type in nearly every system Kepler surveyed. They are more common than rocky planets. They are far more common than gas giants like Jupiter. And every one of them, if it follows the basic structural template of Neptune, has the same internal architecture. A thick hydrogen-helium atmosphere on top, a layer of supercritical fluid below that, a water-rich mantle, possibly containing superionic ice, a rocky core at the center, which means that the most common solid in the universe is probably superionic ice, not normal water ice, not rock, not metal, the strange phase of water that conducts electricity, that locks oxygen in a crystal lattice while letting hydrogen flow free, that we only confirmed in a single laboratory in 2018. Most of the solid material in most of the planets in our galaxy is something we have never observed in nature, something we have only created in lasers, for billionths of a second, something that exists in vast quantities inside Neptune. Neptune, in this sense, is not just a planet. It is the prototype. It is the local example of the dominant planet class. If we ever want to understand the rest of the galaxy, we have to understand Neptune. Neptune is the test case. Neptune is the only sub-Neptune class object close enough for us to ever physically reach. And we have not been there since 1989. Think about what that means. Think about the gap. The most common type of planet in the universe, the kind we should know best, the prototype of trillions of worlds across the galaxy, sits at the edge of our solar system. We have visited it once, with one probe, for 12 hours, 36 years ago. Everything we know about sub-Neptunes, all of it, derives from that one flyby, plus theoretical models, plus observations of distant exoplanets that are too far away for us to ever visit. If we want to know what is happening on a sub-Neptune around another star, 300 light-years away, the closest analog we have is Neptune. Same kind of atmosphere, same kind of mantle, same kind of internal heat, same kind of magnetic field, same kind of trap diamond rain layer, same kind of superionic ice. Neptune is not just a destination we have failed to visit. Neptune is a missing chapter in our understanding of the galaxy. Until we go back, with a real mission, with instruments designed for the questions we now know to ask, our understanding of the most common planet type in the universe stays incomplete. And there is no probe on the way. And there is no probe being built. And the trip would take a decade, even if we launched tomorrow. And the planet itself, when we finally arrive, will do what it has always done. Pull us in, take what data we can give it, and then send us outward, on a course we cannot reverse, into a darkness that does not let go. Neptune is not the end of the solar system. Neptune is the beginning of the part of the universe we cannot reach. Closing, let me leave you with what we have walked through tonight. An atmosphere moving at 2,100 kilometers per hour, faster than the speed of sound, with no clear source of energy. An internal heat output 2.5 times what the planet receives from the sun, generated by something inside that we still do not fully understand. A planet with no surface to land on, anywhere, at any depth. A pressure gradient that climbs from 1 bar at the cloud tops to 700 gigapascals at the core, crushing every spacecraft that descends. A diamond rain layer confirmed by laser experiments at SLAC in 2017. A superionic ice mantle confirmed by Lawrence Livermore in 2018. The most common solid in the universe, conducting electricity, generating a tilted magnetic field nothing else can produce. an escape velocity of 23.5 kilometers per second from the cloud tops, unreachable by any vehicle that has descended. A captured retrograde moon called Triton, slowly falling toward destruction, with geysers of nitrogen erupting through its frozen surface. A 4-hour communication delay, one way, between Earth and the planet. A 36-year gap since the last and only spacecraft to visit, and no probe currently on its way. All of this found or inferred from the data of a single flyby in 1989 by a spacecraft that could never come back. Voyager 2 is still moving. It is now in interstellar space, more than 130 astronomical units from Earth, traveling south, away from the plane of the solar system, on a trajectory that Neptune's gravity bent into permanence. The probe will fall silent within a decade, when its plutonium runs out. The signal that takes 19 hours to reach us today will, within the next 10 years, simply stop arriving. And when it stops, Neptune will once again become a planet humanity has never visited. The numbers will still be there. The cloud images will still be there. The Triton geysers will still be there. We will still have the data. But the connection, the live channel, the one continuous signal from the only probe that ever made it that far, will be gone. The next message from Neptune, when it comes, will come from a probe that has not yet been built, on a launch that has not yet been scheduled, by a generation that may not yet exist. And until then, the planet sits in its dark corner of the solar system, 4.5 billion kilometers from the sun, doing everything it has done for 4.5 billion years, heating itself from inside, spinning faster than sound, forging diamond in its mantle, holding Triton in retrograde, conducting electricity in a layer of ice that should not exist, waiting for the next thing that arrives, and keeping it. Neptune may be the cleanest one-way door in the outer solar system. We have known this since 1989, and we still have not been back.